Hey, Dr. B here, and let's take a look at acids and bases. These are things that change the pH of water. Have a look at these substances here and tell me if you think they're acids or bases. Oranges contain things like citric acid, things like that. They are acidic. Lemons, acidic, same reason. Lemonade, well, you got some sugar added, but that won't change the pH appreciably, so that's also acidic. Tea, tannic acids, things like that. Acidic again. Milk and magnesia, magnesium hydroxide, that's a base. Baking soda, no hydroxide, and yet it's basic as well. It'll raise the pH of water for another reason. Batteries, really they can be all types, right? Alkaline or lead acid, so either. Milk, you might think it's basic, maybe a little slippery, but if you check the pH, it checks in about below 7, just a little bit, therefore acidic. Baking powder, similarly no hydroxide present, but it is basic. Vinegar, that's acetic acid present in there, so acidic. Those tomatoes are acidic. What about the oil that's in the top layer there? We shouldn't say 0 because that actually means a pH of 0 would be a strong acid, but we can say there's no pH there since it's not an aqueous system. And that should point out something important. There are plenty of things in the world that are neither acids nor bases. You need an aqueous system in order for it to work. So, acids lower the pH of water below 7. Bases raise the pH of water above 7. So we can define an acid typically, then this is the Arrhenius definition, as something that has H+, but it could also be something that doesn't have H+ in it. For example, carbon dioxide. And yet it reacts with water to lower the pH, so it's anything that either releases H+ or creates it when it's added to water. A base similarly either releases hydroxide or creates it when it's added to water. So it either has it to begin with or it makes it. Water itself is worth looking at. It's H2O, which means it's HOH, but it's worthwhile to consider if those bonds are covalent, meaning shared, or ionic, meaning that this thing is an ionic compound. Now, greater than 99.9%, this is covalently bonded. This water is not a salt, if you will. It's not an ionic compound. But it is just a tiny bit. After all, there's an equilibrium here. A tiny bit of it does dissociate, and since we live on a watery planet and we are mostly water ourselves, that number has been measured precisely and found to be, if you have pure water, and you can calculate that as being 56 molar. Although that's a little misleading since it's not a solution to begin with, right? It's just pure water. But, that's a lot. But this would be measured to be 10 to the minus 7th moles per liter in water. That's also got to be 10 to the minus 7th moles per liter. And somebody had the bright idea, for better or worse, to call that crazy low number just simply pH 7. So, the POH can also be called pH 7. So pH means the power of hydrogen, and that 7 doesn't mean 10 to the 7th, it means 10 to the minus 7th molar. Similarly, the power of hydroxide is 10 to the minus 7th molar. And if you have a little background in equilibrium, we can go ahead and calculate it, right? And those are the pHs. If you're less than 7, it's acidic. If you're above 7, it's basic. The equilibrium constant expression, you might have remembered to omit solids and liquids, so we're just going to have it be over nothing, right? It'll be the H+ concentration times the OH- concentration. No coefficients that are greater than 1, so we don't have any funky exponents. And we know that it punches through to 10 to the minus 14th molar. Each of them are 10 to the minus 7th molar. That's known as Kw, the equilibrium constant for water. It allows us to calculate certain things. If this goes up a little bit, that's got to go down a little bit to compensate. Therefore, let's review some exponent math and solve some problems. There's what we just said. 10 to the minus 7th times 10 to the minus 7th is 10 to the minus 14th. How about this? 10 to the third times 10 to the minus 7th. Little typo there. Well, I guess 3 minus 7th, that'll be 10 to the minus 4th. 10 to the third times 10 to the 7th. That's 10 to the 10th. 10 to the minus 3 times 10 to the minus 11. Yeah, that's 10 to the minus 14th. That would be a possibility for an aqueous system. And if it's 10 to the 5th over 10 to the 3rd, well, then we'll subtract, and that's 100. Since they always punch in to multiply through to equal 10 to the minus 14th, we can, given one of these, we can solve for the other three. If it's 10 to the minus 7th, that's plain old neutral water. The hydroxide will also be 10 to the minus 7th. We'd say the pH is 7, and the pOH is 7. That is neutral. Suppose, however, that the hydrogen ion concentration was 4 orders of magnitude higher. That isn't just a little higher, that's a lot higher. That means that this must compensate to go way down to 10 to the minus 11th, and therefore we have got a pH 3 solution. That's an acidic, and the pOH would be 11. Try this one. I think the hydroxide would be 10 to the minus 9th. I think the pH is 5. I think the pOH is 9. And finally, if this is crazy low, well, then that one has to be much higher. And here we've got a pH of 13. That is a basic solution where the pOH would be 1. Finally, let's solve a problem. Find the hydroxide ion concentration if H plus is 3.0 times 10 to the minus 2 molar. Well, I could estimate that somewhere in the realm of a pH of 2, but it'll be offset by that. So that's the formula I'd use. This is always true, and we've got one. We'll plug in for the other. So throw that in. We can now solve for hydroxide, and when we do, we find that the hydroxide concentration is about 3.3 times 10 to the minus 13th molar. It didn't ask for the pH, and I sort of thought it was going to. It's asking for hydroxide ion concentration. That's it. And there it is, an exceedingly low number. This is an introduction to acids and bases.